So let's talk about the operational aspects of shallow compaction. When you decide the equipment what to use, there are many variables that controls the densification of the soil. For example, the size of the compactor and mass of the compactor, like how heavy it is, and operating frequency and the frequency range. So is it heavier always the better? So then if it's big, then it's gonna cost more money to land it. And characteristics of the soil, initial density and grain size distribution and grain shape and the water content. So depending on this, you will choose the different equipment. For example, if it's fine grain soil, you're gonna have to use the compactor with a kneading effect. And if it's granular soil, then you may want to use the vibratory compaction. Construction procedure. So number of passes of the roller. So then if you pass just back and forth and more, it's gonna densify the soil, but it's gonna slow down the construction process. So there should be a threshold number of passes. So above that, the density of the soil does not increase that much. So then you have to find an optimized number. And lift thickness too. The thinner is better. So, but then in that case, you have to then it increase the number of layers. So then it increase the project duration, and it costs the money. So we have to find the optimum lift thickness, and the frequency, operation vibrator, and the towing speed. Actually, the lift thickness is depending on the equipment to choose, and the frequency also is a equipment characteristic. And towing speed, slow will be better, but also it's related to the cost and the project duration. So the operating frequency. Normally, for heavy vibratory roller, the frequency is optimum frequency is about 25 to 30 hertz. But compacting effort does not vary significantly in the range of 25 to 50 hertz. So I think within this range, it's okay to use any frequency. In previous study by Forsblad 1977 for vibrating rollers, compaction with large amplitude and a small frequency or the low frequency gave better results than the combination of the small amplitude and the high frequency. So if you look at the dry density curve with different vibrating frequency, so this is in the unit of the CPM. CPM stands for the cycle per minute. So the 6 cycle per minute is the 1 hertz. 60 is the 1 hertz. So 25 hertz is about 1500. So this is 25 hertz is the 1500 CPM, and the 50 hertz is about here 50 hertz. So you can see the many of the rollers are within this 25 to 50 hertz range, and it's in the maximum, the optimum frequency is about 30 to 40 hertz. And roller travel speed or the towing speed for a given number of passes. You can see roller coverage and the speed is here. As you decrease the towing speed, so it slowly moves the roller so that you have a higher dry density for the same number of passes. So for heavy clay, the dry density is about here 1.64, right? 1.6, 1.7, and the well-graded sand is more than 1.9. And also here in the sand too, as you decrease the velocity or the speed of the tow, then it increases the dry density. And number of roller passes. So when compacting, compaction past 5 or so, when the number of passes is more than 5 or so, there's not a great increase in density. So when you look at this dry density curve, this is the dry density, vertical profile of the dry density with respect to the depth. So 2 roller passes and 5 passes and 15 passes and 45 passes. You see that the 5 passes, and you have a 105 pound per cubic feet, and here also about 105, and it's about 105, right? But it becomes a little bit wider, right? But it increased the dry density overall because of you're putting a lot of energy, but the increment, so the change in dry density is not that much as the number of passes is more than 5. So typically people use the 4 to 6 passes for the design. So vibratory rollers, minimum 4 to 6 passes, but if it's a saturated sand, then it's recommended to use the more than 15 passes. And if you look at this graph here, after 4, the dry density increases, but it can approach to asymptotic value. Here, here. So I think a minimum people use the 4 passes, depending on the lift thickness and depending on the equipment type. You can use the 6 passes or the 8 passes. Static rollers and roller equipped with the ship foot or the pad foot drum, minimum it requires 4 to 8 passes. I think because it has a low coverage and because of the protrusions with the leading effect. So another graph showing the similar result, the dry density versus the number of passes. And so 1, 2 is the clay sand. So this is a coarse grain soil. The same soil. And 3 and 4 is the CH, so the highly plastic clay. C and the CH. And the difference between the curve number 1 and the curve number 2 is that in number 1 they use the 8-tone drum and the vibration, and in number 2 they use just static and 1.5 tone. So you can see the difference because they use the vibration that increased the dry density more, and also the mass of the drum was much heavier than the case 2. And you can see that the optimum water content was because it has a higher compactive effort. So the EC is much higher, so that the water content was lower than the lower static, lower compactive effort case. And 3 and 4, so 3 has a kneading effect with the ship foot and 10 tone, so it's a much heavier and the kneading effect. And curve 4 is just a normal static and the 1.2 tone, so it's a lighter drum, so it has kneading, and this has the vibration. And even though the standard Proctor test, the optimal water content is similar, okay? But in the lab, the optimal water content was much smaller in the case you apply the higher compactive effort. One notice that people also typically perform tests on a selected section to decide the number of passes in the field. So it's kind of a field pilot test before they decide the number of passes. And too much number of passes can cause the crushing of the particle at the soil compactor interface, and also it can cause the undesirable stratification, and also it can generate preferred shear plane. and the overall permeability is affected. So we don't want to use too many passes. Then depth of layer, so-called lip thickness. Depth of the compacted layer is a function of applied pressure. So if your compactor or the equipment can apply the higher pressure, then the thickness also increases. But this applied pressure is also heavily affected by the type of soil. According to the previous study, the vertical dynamic pressure by the vibratory compaction is for the sand, it's about 5 to 100 kilopascal, 50 to 100 kilopascal. And for the clay, it's about 400 to 700 kilopascal. So why is the vertical dynamic pressure of the compaction lower in the sands than the clay? Vibration reduces the friction between the sand particles, thus the particles rearrange themselves readily, so it requires less pressure or less force to rearrange the particle to the denser state. But this effect is very low in clays. So this graph shows that the pressure range recommended for sand. So here hatched area is for the sand, and this is about 50 to 100 kilopascal. And for the clay, it's about 400 to 700, right? So 700 kilopascal is the vertical dynamic pressure for the clay. So vibrating plate compactor with very lightweight, so that it has the optimal range of the thickness about I think it's about 20 centimeter. But let's say that compactor 5. Compactor 5 is a vibrating roller with a 3.3 ton. Then it can be like this, so that the lift thickness with this equipment can be as high as 60 centimeter. So heavier equipment, you have a higher lift thickness or a thicker lift, because you have a higher compactive effort, and it can also transfer the load to the deeper depth. So it's small, and then we have only this much of the lift thickness, but heavier drum, then you have this much of the lift thickness with this proper pressure range. So then, what will be the relative density change vertically before and after the compaction? Let's say that this line is the relative density before compaction, and after compaction it will increase like this, so that you have a certain amount of the limitation. So the compaction affects to only 3 feet. 3 feet is about 1 meter. But one thing that you want to notice is that one issue in cohesionless soil, the compaction close to the surface is very difficult because of lack of the confinement. So you can see that in this area, the relative density near the surface is even below the relative density before the compaction. And for the multiple layers, so you can draw the same kind of a curve in layers. Then if the maximum lift thickness for dry density of 75%, let's say that 75% is our target dry density, target relative density, then you can draw the line at 75, and you just overlay this density graph. So then here the intersection should be larger than the 75, and this gives you the minimum allowable, or the minimum lift thickness, the maximum lift thickness for that. So here in this case, it's about 18 inch. Okay, the special case, the compaction at the freezing temperatures. Frozen soils are strongly bonded, thus they are hard to compact. If it is a must to compact, if it's the unavoidable condition in winter, previous study recommended use for A to use the dry coarse material instead of just wet material, and place and compact without delay, because if you wait, it's gonna freeze very soon. So for example, at minus 10 degrees Celsius, gravel may freeze to a depth of 5 centimeters within 2 hours. And recompact and regrade the surface during the following warm season. So you wait until the next summer and you do it again. Or you can add the calcium chloride, which lowers the freezing temperature, and so that it doesn't freeze during the compaction. But because you're adding the chemicals, you have to be aware of, or you have to be careful of the possible side effects with the environment effect and the engineering property, if any possibility in changing engineering properties of the soil. Because if there's a clay, then this addition of the salt will affect the clay behavior. And special considerations for specific materials. If the degree of saturation manifests itself differently in free draining sands and gravel than in clay, if the sand and clay is very permeable or has very large grain size, so that when you add the water, the water just falls through it by gravitation. So it doesn't hold the water as we want for the targeting water content. Then the degree saturation will be changed. So the surface tension in particle partially saturated cohesionless soil increases frictional resistance against compaction. In this case, it is therefore the better to compact in completely dry or fully saturated condition. Then, so in the case of the very permeable and very large size grains soil, granular soil, then it will be very difficult to have homogeneous water content because of the gravity. And clays and silty clays are very sensitive to the placement water content. And this also applies to the lime stabilized soil. And in this case, use a ship foot roller or the pad foot roller and just do the compaction very fast, rapid compaction. Applicability and the production rate. So this is the table showing the applicability of the compaction equipment. For example, a smooth roller, static or vibrating, the well-graded sand, it's more suitable for the well-graded sand across the rock and asphalt. And least suitable soil is the uniform sand. Chip foot roller is static. Then fine grain is suitable for the fine grain soil with more than 20% fines. Dams, embankment, you can apply for that, but it's not suitable for clean coarse grain soil. So this is a good table to refer to in the future. And also it summarizes the equipment characteristic, like vibrating rammer, live vibrating plate, heavy toed, vibrating rollers, impact rollers. It shows the mass and the working speed. So it's about 2 to 4 or the 10 to 14 kilometers per hour, and vibration frequency and the depth of the lift, number of passes, suggested number of passes. And firing, it shows the picture of each equipment, firing rammer and light vibrating plate and light firing roller and impact roller. You can see that as you tow it, it's gonna apply some impact to the surface. And heavy self-propelled roller, heavy towed vibrating roller. So it has also the protrusion, so it has, maybe it can be called as a ship's foot vibrating roller. And the production rate or compaction capacity can be calculated very simply, and it assists in selection of the most economical compaction equipment. So the production rate P is defined as best, PEST, over N times 100. So here the B is the drum width. So if you have drum like this, then this is the B. And the efficiency factor is E, and the S is the rolling speed or the towing speed, and T is the layer thickness, and N is the number of passes. So here the efficient factor is to account for the overlap between adjacent passes. So if your drum is going this way, and then it comes back with some overlap this way, then this is the overlap, right? And also it accounts for the time required to change the direction as you go back and forth. Select efficiency. So typically people use the efficiency factor 75 to 85%, 0.75 to 0.85. So then production rate is because you apply the you multiply the meter and meter per second and the meter, so that you have production rate of the cubic meter per hour or cubic meter per minute or cubic meter per second.